Good morning, everyone. Uh, so just a reminder, I have an office hour today at 11 a.m. You can find the Zoom room on our campus page. Okay. Office hour, 11 a.m. If, if you have any questions, just drop by. And last time we stopped at an example of the integral, well, of uh, a motivated examples of the integral test. Comparison test. So we have compare. So right, that's what I drew last time. So we have a function y is equal to 1 over x, and we have a bunch of small rectangle. This 1, 2. So this point here is 1. Represent a1 is equal to 1, and then the second rectangles also use the right side as the height of the left side as the height of the rectangles. This represent a2 is equal to 1/2. Then there's a3 is equal to 1/3, 3, 4, and right. And then you can continue for all possible n. And we conclude that because for each of these small rectangles, it's always greater than the area of each one of these rectangles is always greater than the area under the curve on the same interval, in the same interval. So we have concluded that the sum 1 plus 1/2 plus 1/3 plus 1/4 plus dots, this is the harmonic series, is greater than the area of y is equal to 1 over x on 1 to infinity. Any questions about this conclusion here? Okay, and then the area under of y is equal to 1 over x from 1 to infinity is just an integral. To infinity, this is an integral, but it's a indefinite integral, 1 to infinity of 1 over x dx. And this is equal to, from the definition of the indefinite integral, this is equal to the limits as t approaches infinity of the integral 1 to t of 1 over x dx. And then this is equal to, because the integral of 1 over x is natural log of x. So it's a natural log of x evaluated from 1 to t, and take the limits and let t go to infinity. And this is equal to the limits as t approaches infinity of natural log of t. Well, I should put absolute value here, but it doesn't really matter because well, because they're all positive numbers. And then this is, and then if you plug in both endpoints, you get the limits of natural log of t as t approaches infinity, and this guy goes to infinity. This is the area under the curve, on the interval 1 to infinity. And in the meantime, we have the harmonic series, the sum of 1 over n, is greater than the area under this curve. So we have the harmonic series is greater than infinity. So that just means the harmonic series, its divergence. Because if it's convergent, then it must be a fixed number, but a fixed number can never be greater than infinity. Let's any questions about this? Okay, let's take a look at another example. Now this time, let's study this series, the sum of 1 over n squared. Right. And again, if we try to use the partial sum to calculate this series, then you will realize we don't really have any formulas for the sum of 1 over n squared. So there's no any simple formula to calculate the sum. But although we can't really calculate the exact value of this, we can still determine whether it's convergence or divergence. Now this time, because it's 1 over n squared, let's compare it with let's compare it with the integral of 1 to infinity of 1 over x squared dx. Just like it's similar to what we did for the harmonic series sum of 1 over n. So again, let's draw a graph. Y is equal to 1 over x squared. And we can find the corresponding points, corresponding value of the sequence on the curve. Like when n is equal to 1, you get a1 is equal to 1. This is corresponding to 1. When n is equal to 2, you get a2 is equal to 1/4. And then a3 is equal to 1/9. A4 is equal to 1/16, and then you can do it for all the possible n. Now this time, instead of using the left side as the heights of the rectangle, we'll use the right side. So so we'll right. So we will use the right side as the height of rectangles, and then use the rectangle roof, So the harmonic series, well, not the harmonic series, this series square, the sum of 1 over n squared is equal to the area of all the rectangles. So just these parts. And then we can write this. Well, we instead of let's see, if we compute the area of the rectangles from the second rectangles, then right, if we just cover the first rectangle, if we just ignore the first rectangles or the first term in this series, you will see that this is less than, this is greater than 1/4, which is the area of the second rectangles, plus 1/9, the area of the third rectangles, plus 1/16, the fourth, and then so on. And this is just the original series. without the first term, without the very first term, n squared. Now n start from 2 plus to infinity. And if we add the first term to it, you get 1 plus this. You get 1 plus this indefinite integral is greater than or equal to 1 plus well, the series, and then this is the original series, 1 over n squared, n from 1 to infinity. And then if you calculate this indefinite integral, you get 1 plus 1 over x squared dx from 1 to infinity is greater than or equal to 1 over n squared. And then in the meantime, this integral is equal to the limits. Put it here. This integral, this indefinite integral dx is equal to the limits as t approaches infinity. The integral from 1 to t of 1 over x squared dx is equal to the limits as t approaches infinity of negative 1 over x from 1 to t, and is equal to the limits as t approaches infinity of negative 1 over t plus, let me see, yeah, plus 1, because it's minus negative 1. And then this is equal to 1. There's a sum notation here, summation notation here. So that means this number, this series is less than a fixed number, 1 plus 1. One is from here, and the other one is from the indefinite integral. So this is less than a finite number 2. And we know that this series is increasing. It keeps increasing, and the term in this series getting smaller and smaller. So we have reason to believe this series is actually convergent. Now these are just motivation. There will be a formal theorem for these two cases. And then I think one question you may ask here is that why I choose to use the left side instead of the right side as the height of rectangles, as what we did in the last example. The main reason is that if you use the right rectangle in this case, you will get the series is greater than you get if you use the left side. As the height of the rectangles. Like this, like what we did for example 1. Then the result you will get the sum of 1 over n squared, and from 1 to infinity. This is greater than the integral from 1 to infinity of 1 over x squared dx. And this we just calculate is equal to 1. And this result doesn't tell you anything about the convergence of this series, because all you get is you have a series and it's greater than a finite number. And there are two cases here. The first case is that this series converges to a finite number that's greater than 1, or this series convergence, this series divergence, and you get a sum that's infinity. Infinity is also greater than 1. So you can't really draw any conclusion from this inequality here. Not determining whether 1 over n squared is divergence or convergence. from the inequality, this inequality. And that's why we choose the other side of the rectangles. Any questions or confusion or comments?
Can you go back to the to your last slide real quick?
Sure.
Excuse me, I do have a question.
Which part?
So at the very beginning, when you have the first term outside of the integral where it's 1 plus integral 1 to infinity of 1 over x dx. So like I understand that the 1 is like the constant of like your first rectangle, like the area of the first rectangle, but would you be able to pull out the first term of like each series that you do regardless of like is that something you do all the time, or is it like a special case for like this integral that we're working with?
I think you can do it all the time because it's one of the conclusion. I don't remember which class, but I mentioned in class that you can remove a finite number of terms from the series. It doesn't change the convergence or divergence of the series. Because here, all we care is whether the series convergent or not. We don't want to calculate its sum.
Okay, perfect. Thank you.
Any other questions?
Yeah, so on that same slide, right, in the top right, when you did the sum of 1 over n squared is less than 1 plus 1, was that because we added 1 to the beginning of that sum and then you had to get it to the other side?
Yes.
Okay, so why wouldn't it be 1 minus 1?
Where's 1 minus 1 from?
Or because it was added from one side, so wouldn't you have to subtract it from the side it was on the sum?
I think this integral is only greater than the sum that starts from the second term. And then if you add 1 to both sides, then you just recover this inequality.
Oh, okay. So you added 1 to both sides instead of, okay, yeah. I thought you just added it to the one side.
Well, if you are doing subtraction, you would get this guy minus 1 is greater than that. But it's not true.
All right.
Because we start from this. And then we add 1 on both sides.
Okay, sweet. Thank you.
Yeah. Any other questions? Right. So this, although we didn't calculate the sum of this series, but someone did, like probably a couple hundred years ago, or maybe even older than that. This sum, this is not required, but I just want to write it here. This sum is equal to pi squared over 6. I think it was probably Euler did that. So it's probably, let's say, probably 18th century. Well, these two motivated examples give us the very first convergence test for the series. It's called the integral test. So suppose f, function f, which is the function that is corresponding to the series. We have seen it from example 1 and example 2. In example 1, it's 1 over x, and in example 2 is 1 over x squared. So suppose this function is continuous, positive is required. And decreasing. Decreasing function on 1 to infinity, or something to infinity, or a to infinity, for example. A is greater than 1, greater than or equal to 1. So as long as it's decreasing after a certain number, then you can use the integral test. And an is equal to f of n. Then the series, let's see, the series sum of an is convergence if and only if the improper integral is convergence. The sum of 1 to infinity of f of x dx converges. So basically, if you have a function, you have a positive decreasing function on a infinite integral. Well, continuous positive and decreasing function on an infinite integral, and an is equal to f of n. Then basically, the test is that the improper integral, if this converges, f of x dx converges, then well, yeah, this is just one side implication. So if it converges, if the improper integral converges, the series converges. If the improper integral diverges, then dx diverges. Then the series also diverges. And then from this theorem, we can relate the convergence and divergence of a series with the convergence and divergence of an indefinite integral, what's called improper integral. And just as I mentioned in the theorem, you don't have to, f doesn't have to decrease on the whole interval. On 1 to infinity. As long as it's decreasing after a certain number, certain finite number, as it decreases. And stay positive. After a finite number. The integral test is valid. So that means the integral test is not only valid for the case like, for example, it's not only valid for the case like this, and it's also valid for the case, for example, the function first increases, but it decreases after a certain number, after a finite number, like if it decreases from here, like for example, this is 1, this is 2, and if it decreases on an infinite interval or after a finite number, then you can also use integral test for this function or the corresponding series. Even you have some oscillations before, and it doesn't matter how oscillatory at the beginning, as long as after a finite number turn it stops oscillating and starts decreasing, then you can always use the integral test. For example, if this is 5 and the function decreases after 5, then and the function stays above the x-axis, the function is always positive on the after 5, then you can use the indefinite. You can use the integral test. So all these cases, integral test, the integral test is valid. So f of x. And for continuous, well, for differentiable function, f, a function is decreasing. For continuous function, this f of x is decreasing. Well, for differentiable function, my bad. F of x decreases or is a decreasing function is equivalent to the f prime of x. The first order derivative is less than 0. And this will be a useful tool for us to determine whether the function f of x is decreasing in the integral test. So let's take a look at an example. Let's try to determine whether the sum from 1 to infinity of natural log of n divided by n converges or diverges. So as you can see, this series is complicated. And if you try to use the definition of convergence and divergence of this series, in which you calculate a partial sum and try to calculate the limits of the partial sum, you will you'll find calculating the partial sum of this series is very difficult. But since we have learned integral test, we have learned one test for convergence. We can try to use this test. Solution, use the integral test. We have f of x is equal to natural log of x divided by x. And in order to use integral tests, we need to make sure f of x is want to show f of x is positive, continuous, or continuous positive and decreasing on some interval on, like, for example, let's do a to infinity, where a is a positive number greater than or equal to 1. Well, yeah, a is greater than or equal to 1. So let's first see the continuity of this function. This is easy to check because natural log of x is continuous for every positive interval, for every interval like this, h infinity, because the only point that natural log of x is not continuous is the x is equal to 0. But since a is greater than or equal to 1 here, so natural log of x is continuous. And x is also continuous from a to infinity, or 1 over x. Well, so this is just the ratio or the fraction of two continuous function. So f of x is continuous. You can say there's no undefined points. For f of x on the interval a to infinity, where a is greater than or equal to 1. And both functions are continuous, so it's continuous. And then positivity, this is also easy to check, because natural log of x is positive as long as x is greater than or equal to 1. And in this case here, because we consider the interval a to infinity, and a is a positive number, it's a number that's greater than or equal to 1. So natural log of x stays positive, and x must be positive because, well, because a is greater than or equal to 1, so a must be greater than 0. And this is also also easy to check. Log of x is greater than 0, greater than or equal to 0. X is greater than 0 on e to infinity, with a greater than or equal to 1. So these are all easy to check in the in your homework assignments or the test. If it's easy, then you don't need to repeat these things. You can just simply say that this function is continuous and positive on some interval, on interval like this. Then you can, and then after that you can proceed to try to determine whether it's decreasing, whether it's a decreasing function on that interval. Right. I'll continue to check if it's decreasing. Since we have f of x, let's see. We have f of x equals natural log of x divided by x. So f prime of x, use the quotient rule. This is equal to natural log of x prime times x minus x prime times natural log of x divided by x squared, and is equal to, so natural log of x prime is 1 over x, that's 1. And the second term is 1 minus natural log of x divided by x squared. And when when 1 minus natural log of x is greater than, is less than 0, f prime of x is decreasing. And then you will need to solve this inequality with respect to x. So from here you get x is greater than, well, natural log of x is less than 1, and x is less than e. So when x is, one sec. Yeah, my bad. This is natural log of x is greater than 1, because you can move this part to the other side, or you just add natural log of x on both sides. You get natural log of x is greater than 1. So x should be greater than e. Right. So when x is greater than e, f prime of x is decreasing. X greater than e, if you write it as an integral, it's e to, well, it's e to infinity. So we can use the integral test for this series. This is parentheses. And if you want to write it, if you want to have a form that's exactly like the integral test, you can maybe start from 3 to infinity. As long as you have a, as long as this number is greater than e, then the function is always decreasing. But you get the point that f prime of x it's decreasing after a finite number. And that's the case when we can use the integral test. Praise it. Three to infinity or 4 to infinity, as long as this number is greater than e, it's safe. And this is when we can use the integral test for this series. So using the integral test, we need to calculate the improper integral 1 to infinity of natural log of x divided by x dx. And this is equal to, by the definition of the improper integral, this is equal to the limits as t approaches infinity of the integral of natural log of x divided by x from 1 to t dx. And if you use the u substitution here, you let u be natural log of x, then du is equal to 1 over x dx. And then this becomes the limits as t approaches infinity of 1 to natural log of t of u du, right? Because you can consider this as natural log of x times 1 over x dx. So in u substitution, this is u and this is du. And then this is equal to the limits as t approaches infinity of 1/2 of u squared. Yeah, in the meantime, the lower bound becomes 0 because natural log of 1 is equal to 0. And if you integrate this function u, you get 1/2 u squared from 0 to natural log of t. And this is the limits as t approaches infinity of natural log of t squared divided by 2. And then this guy is equal to infinity because we know the natural log of t goes to infinity as t goes to infinity. So natural log of t squared, the square of the natural log of t, also goes to infinity as t approaches infinity. take integral from each infinity. Because this function, I think this function is not increasing at the beginning. It's not decreasing at the beginning. I think this function that looks like this. And if you use the if you want to show that it's decreasing from 1 to infinity, then you will fail. So you need to find a larger number. Does that answer your question? Or you were asking something else?
Can you hear me?
Yes.
Okay. So we always adjust the sum, right? Because we had to find that a of n was decreasing, but it's only decreasing from 3 to infinity. So why don't we change the integral bounds as well, is my question.
Oh, okay. You can change it. It doesn't really matter, because a finite interval, just like for example, if you do 3 here, 3 to infinity, if you add this part to the original, if you add this part, it doesn't change whether this series, whether this improper integral is convergence or divergence. So what? So
Okay.
then I just use 1 to infinity. You can use 3 here. It doesn't matter.
So it's just because we're not actually finding the sum. We don't really care.
We're
We
not
just want
trying.
to know if it's a number, right?
Yeah, we just care about what we just care whether it's convergent or divergent. We don't care about the exact value
makes
of
sense.
it.
Thank you.
Yeah. Yes, you need to adjust the bonds when you use your substitution. Sorry. Here's here. Thus, the series is convergent, is divergent. And I'll just point out here, the bonds, you can also change the bond. Change 1 to infinity of f of x dx to a to infinity of f of x dx. This is because all we care about is whether the improper integral is convergent or divergent, and we don't care about what the exact value of it, the exact value of the improper integral. So, any questions? All right. There's one more example from the integral test, the P-series test. P-series refers to the series in this form, 1 over n to the p, where n is from 1 to infinity. So when p is equal to 1, it's the harmonic series. And when p is equal to 2, it's the series we did at the beginning of the class. Yeah, there's no name for this series, not that I recall. But here, the P series refers to more general P, and depends on the value of the P, the convergence and divergence of this series changes. Right. So if P is less than 0, then 1 over n to the P, this term goes to infinity. It's like, for example, if you have, P is equal to -1, then 1 over n to the -1 is equal to n. And as n approaches infinity, this guy approaches infinity. So when p is a negative number, this term goes to infinity. And from the test for divergence, this term doesn't. So this term doesn't go to 0, and from test for divergence, the series diverges. This is the first case. And then when p is equal to 0, now you get 1 over n to the p. The n term in the series is equal to 1 over n to the 0. And any non-zero, the 0 power of any non-zero number is equal to 1. So this guy is equal to 1. And again, as n approaches infinity, this is 1 and it's not equal to 0. And then from the test for divergence, implies the series diverges. And the last case is when p is greater than 0. Now this time, if you try to use the test for divergence again, you will see all the term, this term goes to 0 as n approaches infinity. So we can't get anything useful from the test for divergence. But if you look at, if you consider the corresponding function f of x is equal to 1 over x to the p, then you realize this function is continuous. Like 1 over x squared, or even 1 over square roots of x. It's continuous. It is positive. As long as x is a positive number. And is decreasing. On 1 to infinity. All of these, any one of these functions looks like just the shape of any of these functions on the positive axis always look like this. So we can use the integral test. But we don't have time to finish this integral test. So I will stop here and continue this example on Monday. Any questions before I left? Okay, we'll meet on Monday.
Thank you.
Yeah.